about the homework, which is a concept that's defined in your homework. One of the problems talks about a base for a metric space. And I just want to give you some intuition about why we care about a base. Actually, that's Rudin's terminology. The more common terminology these days is the word basis. Okay? And how many times have you heard the word basis in a math class? What is a basis for a vector space? Okay, lots of ways to describe it, but the operative concept is a basis you build other things from, right? You can build any vector as a combination of basis vectors, right? Okay, well, this is exactly the same, analogously the same concept here. What is a base or a basis for the open sets or for a metric space? Of course, this is the way we describe it in topology. It's a basis for the topology. It's this. You give me any open set, let's call it U, and any point in it, let's call it X. A base, is a collection. It's some collection. And I don't care what collection it is, but it's a collection that has the following property. You give me any open U and any point X inside it. What's true about a basis is there's a point of the basis that surrounds X that's inside of U. Such that, what? For all X in some open U, there exists a V alpha such that X is in V alpha and V alpha is contained in U. For any X in any open U, there is a V alpha such that V alpha lives in between. Okay, now what's the big deal here? Well, the big deal here is I can do this for every point in U, yes? So U can be written as the union of a bunch of basis elements, just by taking the union of V alpha for every point X. With me? Yeah, so in fact, the idea here is, so every open set is the union of base elements. Okay, and your homework asked you to explore this concept. And really, the reason is that there's all these concepts that have to do with the size of a set. So if you have a metric space where the base is countable, then it's small in some sense. If you have a metric space that has a countable dense subset, in other words, separable, which you learned in your homework last week, then it's small in some sense. Okay? And it turns out that if you have a metric space that is compact, well, then in fact, a compact metric space has a countable base. Compact metric space has a countable dense subset. Okay, so these notions of smallness somehow coincide, and they give you other tools for showing that a space isn't compact, right? If you know that a compact metric space has a countable base, and you find a metric space that doesn't, then it can't be compact. Right? Other strategies for showing not compactness. Yes, Jenny? Oh, well, yeah, so this has got to be true for any U, for any open U, right? So, yeah, for any open U. And in general, for a topological space, in order to be a basis, you need it to have the property that there are enough small sets to take care of things. So you want it to be the case that if you intersect two V's and you take a point in between, that there's another smaller basis element inside. The way that you would make that true here in a metric space is demand that these V alphas be themselves open in the sense of having interior, every point being interior. Okay, so the idea of a basis is basically you can build up all open sets from just these. Okay. Now, one basis for a metric space is just to look at balls. That's a basis. We've already seen that. But you could also take other things to be basis elements. Okay, that's a word about bases. Okay, let me say something about connected sets. As I hinted at that here. Yeah.
So in your algebra basis, you wanted to have it be as small as you could, like you throw out the ones that were repetitive. Is there anything like that for a base?
Excellent question. No, there's not a general notion of you can't talk about something that is the smallest basis because they don't necessarily, one small thing doesn't necessarily contain the other, etc. Yeah, so you can't intersect two bases and hope to necessarily get a basis or anything. But there could be lots of different bases for a particular metric space. Yeah. Okay, great. This is the last concept I want to discuss today, and that is connected sets. What does it mean for a set to be connected? So, for instance, if I draw a picture like this, does this set feel to you somehow connected? Yeah, sure, right? But what about this one? Not connected, right? Why? How do we make that notion precise? Well, it turns out it's a lot easier to say what's not connected than to say what is. And I'll show you why. What's true about this set not being connected? Well, somehow I can separate one from the other, right? Yes.
Visually right there with that particular set, it has a finite open cover where the pieces of the open cover have an empty intersection.
Okay, I think
So
you're.
we can cover with disjoint sets.
This is sort of what you're saying, yes? These are open and they separate the two. Yes? Okay. And that would rule out, like this picture, can't I cut this piece into two pieces where this goes in one half and then the other half doesn't contain this boundary? Well, I certainly can cut those into two pieces, but you wouldn't want to call these separated either, right? And your criterion would prevent that, right? You can't put an open ball around this and an open ball around this that don't touch each other, yes? Okay, good. This is actually a good topological definition for separated sets. The book uses a different notion, which is equivalent. And the equivalent concept is you demand, let's say this set is called A and this set is called B. We'll call A and B separated if no point of A is a limit point of B, okay? And vice versa. That's actually, can you see why here that's not true for this A and B? Isn't it true that some points of A are limit points of B, especially if I go from this side towards the boundary? Okay. So that's the concept of separated. So let's make that definition first. So if A and B are, we'll say two sets A and B in X are separated if you're going to demand both of these to be true, A intersect B closure, and A closure intersect B are empty. This is saying exactly